So, hi everyone. Let's start today's lecture. So, today basically I want to uh, discuss how to build a mathematical model from the basic assumptions. So, let's see that how to do it. Okay. First of all, let me talk about what is mathematical model. So, in Hi Subusachi, can you hear me? Okay. Yeah. So today we are going to discuss about mathematical models. We will see that how from the basic assumptions and or laws how can we build a mathematical model. Now, as we have done, as we have seen in the previous class, that what does prediction means and how one can predict through mathematical model, and what the definition of the predictions changes from a perspective of physicist point of view from it uh, from from the deterministic prediction it becomes probabilistic. Now, in mathematical model, what we do, so from some basic laws or some basic assumptions, we write an mathematical equations, and from that equations we want to generate the predictions. Now, is it always possible to predict? No, it is not always possible to predict. But if I change the definition of prediction, as we have discussed, we can actually have some knowledge about the system. Now, uh, so mathematical model, what we'll do. So for many and before going to the actual exact model, so I want to say you that every mathematical model is only a approximate of a real system. So as for an example, as we have all seen a map of the world, so if I ask you, is that map really represent the earth? Can you, Shobhudaji, can you tell me that everyone sees in our childhood that the in the primary school there is a map of the earth where from where we can see where is the seas and where is the lands are there. And if anyone asks you, is that map is exact model of the earth, what you will say? Right, exactly. That is my point. Exactly, that is my point. So actually, the Earth is a round shape object, and I am creating a 2D object to model that things only to get what you have said, that to get the points and where is the seas and where is the lands are there, but it is only approximate. So in every case, whenever we want to we want to extract some useful information, we have to simplify our model in some way. Now that's the thing. So here also, from our basic assumptions, we want to build a model which is obviously approximation model of the system. But if I get the predictions close enough, we will say that is an useful model. Now let's write a population growth model. Population growth model. Now why the population growth model is very important. So as we know that ecosystem, in our ecosystem there is a food chain. So if some particular species gone very high, then our food chain will be disturbed. So that's why it is very important for a population biologist to predict what will be the size of the population. Now, before that, if I ask, as we have discussed, what is our predicted quantity in the population growth model? So that will be obviously the size of the population that I want to predict. Now then, what will be the state of this population growth model? This obviously the state of the population growth model will be the size of the population. Suppose n is the size of the population at time t. At time t. So that is the thing. Now in population growth model, every time whenever we want to write a population growth model, we will write a growth rate equation. What is the rate? So in mathematics, rate is written by dn dt, but don't worry, this is nothing but if in the mathematical term, it is basically, let me write it mathematical definition. It is, but I will explain what does it mean. So limit h tends to 0, so n of t plus h minus n of t h. Okay, I am sharing. Oh, I forgot. So thank you. Now you can see, right? So okay. So in every time so this is the growth rate equations. Growth rate. So rate basically means, so this is the definition of the rate. So it means like that, if I know the population size at t plus h, and if I know the population size at nt, what is the rate at which the population is growing or decreasing? So and dndt basically says per unit time how much the population size changes. So that is dndt. Now this is called differential equation. I want to write a differential equation, but don't worry, this means nothing. That this means that the number of individual increases or decreases per unit time. And in mathematical language, if I want to make sure that this quantity exists for all n, I have to define that quantity as limit h tends to 0, means if I have very too close, if I observe in a very close time interval, then what is the difference in this close time interval h, how much my population increases. That's it. Now you see in okay, let me let me, I think, let me share it again, then maybe. Can you see now? Yeah. Okay. Okay. uh, so now it is feasible. Can you so should I explain again this concept, that what differential equation means, or did you know something about it? Okay, let me again. Okay, okay. So as we know that every population is increased by successively addition by one individual. So every population, so the increment or decrement of the population should be decreased, should be discretized. That means at the some point of time, some number of individuals added to the population by birth, or some number of individual decreased by death. So there could be possibly two kinds of model here. So one is discrete model and one is continuous model. Obviously I will come upon to the thing that the continuous model have some issues in it. So let me first draw what do I mean by the discrete population model, and what I want to get as a prediction. So as I have tried to write a model, and from that model what kind of solution I want to get, I want to take. So I want to take the solution of the time series data. It is called time series data. Suppose it is t, and I am observing in the interval t equal to 0 t equal to t equal to 1 year, 2 year, 3 year, 4 year, 5 year. So this is discrete model. So I want to this is n. Suppose this is 100, this is 200. Now some point of at t equal to, at this is at first t equal to 0 I get 50 number of individuals, then at some point of time I get 100 number of individuals, then at third year I observe 25 number individuals. In fourth year suppose I observe 300 number of individuals, and so fifth year I get 150 number of individuals. So you see the jump from these to this is quite high and it is abrupt. So you can say this is a discrete model of the populations. Now if I want to solve a discrete equations, obviously I written a continuous equation. Wherever you see this differential equation d and dt, it means a continuous equation. So here this is a discrete model, discrete population model. I also built equations which is very crucial for the aspect of the chaos, and it is called discrete model. Now let's see a continuous model. Now in the similar fashion, 0, this is 1, this is 2, 3, 4, suppose 5. Now 0, 1, this much individuals, and this and second year if I observe it only increase by small amount. In third year it's also increase by very small amount. So increase by very small amount. So it continues like that. So by visually seeing, can you Sobhudaji say that between these two graphs, what you can visually say, what is the difference between these two graphs? Right. Okay. Yeah, you are right. But here you think that in mathematical term, what you are want to say that it is a kind of monotonically increasing graph, and it is quite every time, every successive year it is increasing. But here it is not that case. Some year it increases, some year it decreases. And another thing is that the jump could be here very, that the population size between the third and fourth year could be very, the difference between these two could be very high. It is not small enough. But here you can see at every year the number that change is very small. So that is a crucial aspect. So if that is a crucial aspect for a continuous model. So let me write the continuous model. Continuous model. Now let me tell you what a continuous function is first. So continuous function means if I decrease this interval, suppose if I want to measure not in the interval of 1 year but the interval of 1 month, then this increment will decrease further. Suppose instead of this, if I zoom this 0 to 1 interval picture into, suppose this is 0 to 1 year into 12 month, 1 2 3 4 5 6 7 8 9 10 11 12, in 12 month you see this increment. And here suppose this is suppose 50, this is suppose 100, so this will be suppose here 50 and this will be 100. Now in 0 to 1 interval, so 1 month you will see that, in 2 months suppose you will increase that much, in 3 months this much, in 4th month this much. So it will continue like that, and in the end of the 1 year you will observe the total population size is 100. Now you see one thing, that if I in the interval of 0 to 1, that the difference between the population size of the first year and the 0th year is 50. Now if I decrease this interval by 0 to 1 month, in 1 month you will see the decrease is very small. It may be 50 to 55. So as I decrease my observing time period t, my increment in the population size decreases. So that is basically that thing of the continuous model. Mathematically, if I say a function f of t is continuous, when I will say the continuous, if f of t plus dt means the if you say f is the population size, then if t, suppose t is 0, that means at 0th it is 50, and t plus dt, suppose dt is equal to 1, so t equal to 0 and dt equal to 1, then 0 plus 1, so f of 1 means what is the number of population at 1 month, so that will be 55. Now you see f of t plus dt minus f of t, which will be 5 individual. Now if we decrease this dt from 1 month to 1 day, if it decrease further, it will decrease further. So if we decrease from 1 month to 1 day, it will decrease further. So mathematical definition is that a function f will be continuous if I decrease the dt, suppose the dt is tending to 0, then this difference f dt minus ft also tends to 0, then this function will call continuous function. So Buddhaji, could you understand this, why when a function will be called continuous? inter exactly. The difference between the quantity of now you if this is so, so there will be a question. So uh, could the population growth model could be, can we thought it as a continuous model? What do you think? Yeah, it is right, but the reason is very simple reason, because you see that it demands that if I decrease my observing time, the increment should be tends to 0. But you see, for the population, the increment is in discrete step, means only one individual can give birth of a only one individual. That means every time the decrement or increment, that means delta n, if I write delta n is the change in the population, cannot be less than 1, because a individual cannot reproduce a fraction number of individuals. Suppose our individual reproduce 1.5 number of individuals, it is not possible. So that means the change in this nt plus dt minus nt could not be less than 1, and since 1 is not, it is, if it is less than, not less than 1, it will be always greater than or equal to 1. It will be always greater than or equal to 1. That means it can't be approaching 0. How means how much decrease this dt, its lower value is actually 1, so it can't be, its lower value can't be 0. So that's why we can't means in principle we can't write a model which is continuous. Now here comes the approximations. As I say in the beginning, so in the mathematical model we always assume some approximation, we always consider some approximation. So here comes the approximation. So when this approximation will work, now suppose that population size is quite large. Suppose is in current there is a 8 billion human beings. So if some individuals born somewhere, and respect to the 8 billion individuals, so one individual is very small, it looks like that nothing's happened to the whole population. So then we can approximate it, that we can say that relative to the whole size 8 billion, 1 is very small, and it is, it for in the perspective of 8 billion, it is equal, it is tends to 0. Then I can obviously write a continuous equation. Now, so if n is large, but it is not also quite required n large, another thing is very required. So the thing I want to say here, that the increment is very small. Now if there is a large number of individuals, and if that population's individuals do not have any preferred season for the reproduction, no preferred season for reproduction, no preferred season for reproduction. Now you see, if any individuals from the populations at some point of time in the whole year can reproduce, then you see there is so then we can thought that the population is changing in continuous manner, because you will not see that any particular time interval there is a lot of jump in the population size, because in that particular year a lot of the individuals are reproducing. If that is not the case, then we can thought that the population increases by approximately in the continuous manner. And yes, indeed it the case. So for the population of humans and populations of amoebas, populations of yeast could be modeled through a continuous model. So let me put observations from data of Carlson 1930. So it is populations of yeast. And the main reason that these graph can be approximated by the continuous model, because these yeast don't have any preferred breeding seasons. So that means in every time of the year or every time of the day they can reproduce, and we can think that it is grow quite continuous manner. So this is 100, 300, this is 5, 700, this is cells, this is number of days, 0, 5, 10, 15. So every day they 2, 3, 4, 5. Then there is a up to side 10. There is a 1, 2, 3, 4. Then it continues. So it looks like, okay, so it looks like these. So it's like quite not right. So it's no, at 15 days it look like that. Okay, now here why I am drawing 5 dots, because in every one day at the end of one every day they recorded the data, what is the size of the cells, what is the number of size of the yeast populations, and they plot a point and they get this kind of graph. Now if I connect this graph, so it looks like continuously growing. It's not look like that abruptly jump is happening there. It's look quite continuous growth. So it will grow, means if I connect the dots through the line, it will look like a S-shaped curve. This is called an elongated S-shaped curve, or is called sigmoidal curve. Sigmoidal curve and sigmoidal curve. That's the thing. Now, for you can see clearly that these cells, in spite of the fact they are reproducing by numbers, means these definition can be satisfied, but also we can quite easily we can make a continuous model for the populations of the yeast. Now when we will apply the discrete model, so this, okay, when we apply discrete model. Okay. Now when we apply discrete model, so in the contrary to the fact that if there is a preferred season for the reproduction, now what will happen then? Then all the individuals simultaneously reproduce in that period of the time, and if they reproduce that period of the time, and if they have a preferred birth period also, then a death period also, what will happen? Though if you observe at the some point of time of that year, the size of the population will grow very much, right? Could you understand, Subhaji, why for the, if that the individuals do have a preferred season for the reproduction, then or breeding, if they have a breeding season, then the change in the populations will be very abrupt or very high. Maybe suppose at a particular time the all individual reproduces, and if all individual reproduce in one individual, so if suppose in the population n individuals was there at time t, at nt plus 1 it will be twice. So that means the change in the populations will always remain high. So it can't be thought as a discrete continuous model, in the contrary to the population where the individuals don't have any preferred seasons. So that's the main funda of the discrete model and continuous model. Now let me how in the later how I will means graphically show you the discrete model. So it basically, I will say there is a point 0, this is suppose 1, this, then 0 here, 1 here, 2, there will be suppose 3. Now there is a certain decrease, if death is also there, certain decrease. So you can see there is a quite high jump in this. So this kind of model you will say, but you see one thing, so you see one thing, I am drawing a line between these two, but this line doesn't have any meaning, but this line has meaning. It says that if I observe in between these two observations, I will get some point here. But here this line doesn't mean that if I observe in between these I will get some point here, because what, they are only suppose that they are reproducing at the end of the year. So here I will say I will get a continuous line like that. So if I observe, I will say nothing change in the population size remains same, because no one reproducing, that's why. And at the end of the year they all reproduce, so that's why I will get a jump, and it remain constant up to second end of the first year, and the end of the second year I will get a large number of individuals. So it will remain constant in this interval. It is quite it is not like the continuous model. In the continuous model, as I said, that in between two observation, I will, if I say what is the number of population size here, it is not like this. It is actually the point which is in the card. So for only visualization, so how from these populations to this size goes, that's why I am connecting this point. So from 0 to 1, then 1 to this, from this to this, this to this. This is not quite correct. So this is this. That is the thing. Now let's see some observations, some growth patterns. So here there are 3 growth patterns from the weevil populations. So there are 3 growth pattern of the weevil populations. Okay, weevils population. Okay, now let's see. This is from this is a paper I have taken. So this is Fuji 1968. So it is recorded in China. So 0, this is 500, this is 1000, 1500. Suppose this is 5, this is 10. So 5, 10, and it is generations. So as I said, since there is a breeding season, so that's why its generation means the end of that seasons. It is at, this is 0, so at 0 is quite close to this 0, then here some point, then here, then here, or something like that. So if I connect these dots, so here to here to here, so like this is the pattern we will. Now another is that five, this is 10 generations. So it is observed by Udita 1967. So it is 0, suppose this is 100, this is 200, this is suppose 300, from 0 it is here, then it is above 300, then it becomes like that. So it is called, in theoretical term, it is called oscillating around, it's oscillating and try to converge towards the fixed point. Suppose there will be some solution, so it will continue to grow and it will fix there. So this is observed by Udita 1967. And there is another thing that is that seems like it is chaotic for that populations. So it look like this. Look like, okay, this is 0, it's 500, suppose this is thousands, this is 1.5, and this is again Fuji 1968. So this is 5, this is 10. So we first start from here, then it goes above 1000, then again somewhere, then sometimes it remain here, then again it goes higher than 0, higher than, and then lower than this, something like that. So from here to here, then here. So that's how its populations dynamics is. So you can see it is quite chaotic. So it don't has any pattern. So in the above two cases there is a pattern. So it is a continuous growth. The solution converges towards some point, and here you can say it doesn't converge and it doesn't have any pattern. So this is looking like chaotic. So that's all. So that's how we means that's how we characterized a continuous model and discrete model. Now let's see how can we write. Let's write a continuous growth model. Continuous growth model. Continuous. Now, Subodhji, do you understand what is the basic funda between these two model, that the discrete model and continuous model? Okay. Huh. Huh. Hmm. Huh. Right. 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 Yeah. Continuous growth model. Now let's write a continuous growth model. Now, as we have discussed all the things, so let's write. So dn, as we have said, we have to write in such a way dn dt. dn dt is the rate of change of the population. So if I divide the dn dt by 1 by n, what does it will mean? It means, so how much on average a single individual reproduces. So dn dt means how much in time dt, in, if I loosely speak, then in time dt, dn amount of individuals, dn is the total change in the population, size. So suppose some of the individual reproduces, that's why it changes to n plus dn. Now if I say what is the contribution of each and every individuals, so that will be 1 by n. So 1 by n basically means in the population, if I select a random individuals and if I observe that individual, so on average how much that individual reproduces. So this is called average reproduction rate. And if I, since I have worked on the evolutionary game theory some point of my life, so here where you will see this quantity is called the fitness of an individual. So in the Darwinian terms, so fitness is very important. So if some traits has higher fitness than the other traits, then that trait will flourish in the environment. So that way, how you calculate theoretically the fitness of an trait, so in that way, it is, you can call this is the average fitness of that populations. So that's all. Now dn dt, now you see here this quantity 1 by n dn dt, it could be negative as well, because if at the some point of time the birth rate, so it is basically nothing but the average. So let me write it. So it is nothing but the average birth rate minus death rate. So 1 by n dn dt is average birth rate of death rate of a single individual. So then it could be negative as well, because if the birth rate is less than the death rate, then it will be negative, that dn dt will be negative. And it could be positive if the birth rate is greater than death rate. Now if I ask you a question, so what is the what is the maximum negative value this can achieve? That 1 by n dn dt. So it could be -1, -2, -3. So if you understand this, then could you Subodhaji, could you tell me that 1 by n dn dt, that is the average change in the population, so it could be negative, as I say, if the birth rate is less than death rate. Can you say what maximum negative number it can take? Okay, so it is basically, if you think that it is telling about that how much a single individual reproduces, means how much a single individual reproduces, and what is the rate of that single individual, what is the rate of the death of that single individual. So it can't be its magnitude, or it can't be less than -1. That means it can't take the value -2 or -1.5, -2 or -1.5. Let me write it in this way. So if I take the modulus value, or 1 by n dn dt can't be less than -1. Why? Because suppose there is a individuals who can give birth 2 or 3 individuals, and suppose it dies after after reproducing 3 individuals, it dies. Then what will be this quantity? This will be 3 minus 1. So on average, how much it will increase in the population? That is only 2 individuals. So then the dn dt by n will be 2. Now suppose that individual and the death can't be less than 1, because can be greater than 1, because if there is a single individuals, and the only thing it can decrease the population by, if that individual dies, or she dies in the populations, the population will decrease. But we can't think like that it because of that, means a single individual dies twice. It can't be like that. A single individual dies once, that's why it can't be less than 1. So that means what will be the minimum number of this rate? That will be when that individual reproduce no children and dies. Then what will be this rate? His birth rate will be 0 and death rate is 1. So that's why is -1. Could it be 0 minus 2? No, because that individual will only die. It can't be like that it dies twice, because of he dies, the decrement in the population is 2. That can't be happen, because this individual can dies only once. So that's the case. So the minimum value 1 by n dn dt will be -1. So what time left? Okay, so that's the thing. So one thing I only want to say one thing, then I will conclude this class. So this is the my equation. So let us write an unlimited growth model. So in the next class I will say why it is unlimited. I am saying this model is unlimited. So unlimited growth model. So if I write dn dt 1 by n, suppose I measure some populations and it comes out that this average growth rate is constant. Suppose this is r. Okay, this is r. Now this is my equations. So this is my equations, and in Newtonian term, this equation will be called the predictor of the system, because from if I can solve the equation n, in the solve means if I can get the all value of n at, if I say what will be the size of the population at time t, any arbitrary time t, if and q give me by solving this equation, I will say this is my the prediction of that populations. Now can we do that? Can we get a closed form? And closed form means, again I will write this closed form. Closed form means you do have a formula for that, generating that n in terms of t. Now if I integrate it, so if I assume that Sobhusaji you know little bit of integration, but I am doing the integration here actually. So if time t equal to 0 to t, okay, let me like this way, t equal to 0 to tau, so in this side, let me write it in this way to be clear. So integration n equal to suppose 0 to small n dn by n equal to t equal to 0 to tau r dt. So these integrations formula is log e to the e base n, this will be n capital N, this is 0 to n. Now it is not 0 to n, at the, if the populations initially will be 0, then it will always remain 0, because there no one will be there for reproduction. So this is suppose from n0 to n, so this will be n0, this is rt. Now this will be ln n by n0 rt, and so n will be some n0 e to the power rt. Now if you ask me, if I know n0 and this r, I can tell you at, if you give me any time, if you want the population size at any time, if I put the value t here, I will get the size of the population. So this is the called the prediction, and this is called the closed form solution. So this is not only one form, there will be lot of form is there. So that's all. I will in the next beginning of the next class I will again explain these things. So that's all for this today's class. Now if you have any questions, you can ask me. Yeah, it's exponential growth model is same. Exponential growth model, no, if you say the growth is growth is exponential, yeah, it is same, because here you can see the growth is exponential, it is same. Lower. Exponentially, right? Okay. Oh. Okay. Thank you. Friday. Thank you.